Hello. Good afternoon, everyone, and welcome to 19 Washington Square North. This is the intellectual center and home of NYU Abu Dhabi here in New York. My name is Michael Puruganan. I'm a Silver Professor of Biology here in the New York campus, and I also run a laboratory at the Center for Genomics and Systems Biology at NYU Abu Dhabi. And I have the privilege of serving as the academic director here at 19 Washington Square North. So it's a pleasure to welcome you to another academic year here. Actually, I should be welcoming you to another academic year because we're already in the middle of the first semester. But it's a year that promises to have many exciting and stimulating programs here at 19 Washington Square North. So over the course of the academic year, 19 is host to numerous activities from lectures, conferences, and artistic exhibitions and performances. It also serves as a meeting place for students and faculty, and indeed members of the general public to interact and to learn. So a key partner of ours here at 19 is the NYU Abu Dhabi Institute in Abu Dhabi and New York, which has organized many of the activities here. And I want to acknowledge the work of Sharon Hakaken-Bergman, the Director of Academic and Research Programs of NYU Abu Dhabi Institute, who with her staff puts together many of the activities that we have here at 19. So today we're very, very pleased to see all of you at this talk to be given by Professor Ahmed Almheiri, a member of the physics faculty at NYU Abu Dhabi. I actually, the way I roped him into giving this talk, I didn't know he was here on the campus until I bumped into him, I don't know when, and I said, "You're actually here, you should give a talk." So I roped him into giving a talk, and he graciously accepted. Ahmed joined the NYU Abu Dhabi faculty in 2022 after serving for 5 years at the Institute for Advanced Study at Princeton. Before that, he did his PhD at the University of California at Santa Barbara. His research work is at the interface of quantum information and quantum gravity, and has contributed greatly to our understanding of black holes. He has numerous honors, among them, and very, it's something that is bestowed to very few early career physicists. He won the 2021 New Horizons in Physics Prize by the Breakthrough Foundation for his work, and also more locally, the Pride of the Emirates Medal. So it's a pleasure to welcome Ahmed here to talk to us about the secrets of black holes.
All right. Thank you, Michael, for that introduction, and thank you for inviting me to give this public lecture. It's a real pleasure. So I'm going to be telling you about, or rather, I'm going to be exposing the spooky secrets of black holes. I promise that I'm only going to make 2 Halloween jokes. Okay, that's one of them. The other is that back home, I don't dress this way. I dress in the usual Middle Eastern way with a white robe. So for this Halloween, I'm dressed as an American. Okay. So I find black holes to be really fascinating and interesting physical systems, and I'm always happy to explain what they are to people that don't study black holes, and just see the amazement and wonder in their eyes. Just a show of hands, how many of you here have been to talks on black holes? Okay, so maybe like 30% black hole junkies. So I've also been to many talks about black holes. I've made sure to include things that are not usually explained in public talks, maybe because they think it's going to be way over your head. But hopefully you'll leave this talk having learned something new. Okay. Before we talk about black holes, let's talk about the scientific method. So here's a very simple chart explaining what the scientific method is. It has 3 components: observation, theory, and experiment. In observation, you observe the universe, and you notice that there are some patterns. Given those patterns, you try to come up with a theory, let's say, mathematical description of these patterns. The ancient Greeks, when they did this, they stopped at this step. They wrote down a theory that explained the patterns and said, this is the universe. And famously, they've been wrong about many, many things. That's because they missed this last step. Once you write down a theory or a description of the universe, you need to test it. And often you test it in regimes, well, not often, you have to test it in regimes that are don't overlap the observations. Otherwise, you're just confirming what you already formulated. So once you do that testing, two things can happen. So this theory makes a prediction, and once you try to confirm it, two things can happen. One is that it doesn't work. Experiment would then rule out your theory. That would take you back to this theory component. You have to modify or fix your theory, and then conduct the same or different experiments. And if it works, you go back to the observation stage, meaning you use the experimental apparatus that you've built to make new observations outside the regime in which your theory is meant to describe. And then you keep going through this process. Now, I'm a theoretical physicist, so I don't do any actual experiments. Although I do perform a different kind of experiment called a thought experiment, where before you tell the experimentalists to go and confirm or deny your theory, you don't want to waste their time. So what you do is you conduct so-called thought experiments, hypothetical scenarios where you test your theory and see if it makes sense or not. You say, for example, in our discussion today, suppose I jump into a black hole. What do I see? I don't think any experiment in their right mind would jump into a black hole, nor would they send their extremely expensive apparatus into a black hole. So that's what we do. So there are two advantages to these thought experiments. You can push your theories to the extreme. The other advantage is that it's completely free. Okay? Experimental apparatus is usually extremely expensive. Okay, so that's the scientific method. You might ask, what does doing science look like? For an experimentalist, you're often observing the universe far away, or you might be observing things more closely, more locally, and sometimes even within. What do our cells and so on do? And practically, that involves something like this. You deal with a lot of experimental apparatus, and you get to wear these cool shades. Okay. Every now and then, an experimentalist is able to convince funding agencies to fund things like this, like the James Webb Hubble telescope, which can take these spectacular images of the universe. Okay, so that's experiment. What about theorists like myself? Well, all we do is just sit around and think. And we sometimes do this thinking with other people. So we discuss together, getting different perspectives on your ideas from other people. And sometimes we just take walks. Here, this is, sure you've recognized this guy, Einstein, walking with Kurt Gödel on the premises of the Institute for Advanced Study. I think that's the pond there. So there's a lot of walking, there's a lot of discussion, there's a lot of exchanging of ideas. And a lot of this discussion, like in this picture, happens in front of a blackboard, which is often left as looking something like this at the end of the day. Now, this might look like gibberish to most of you. And in fact, it looks gibberish to me too, because this is not physics. Okay. Okay. Before discussing black holes, so we're going to transition to the physics, we need to understand what are the rules of space-time. This starts with electricity and magnetism, it turns out. So here is Michael Faraday, one of the fathers of studying the relationship between electricity and magnetism. These are the rules that govern things that happen in your smartphones, for instance. And he established the connection between electricity and magnetism, how electricity can give rise to magnetic effects and how magnetism can give rise to electric effects. But as he was studying these phenomena, something was missing until a light bulb turned on in one of his students' minds. And that's James Maxwell. He wrote down these equations that unify the concept of electricity with the concept of magnetism and how they talk to each other. What these equations say in words is that an electric field generates a magnetic field, and then that magnetic field generates an electric field, which then generates a magnetic field, and so on and so forth. He found out that this oscillation between the two notions, in fact, describes light. Which is often goes by the name an electromagnetic wave. So it's these oscillating electric fields and magnetic fields. Often when you write down a unifying theory, such as these equations here, surprises come out. The amazing surprise here is that light, as described by these oscillations, actually has a finite speed. It's roughly 700 million, yes, miles per hour, roughly speaking. Okay, but if light travels at a finite speed, and the reason you're seeing me is because light bounces off me and goes into your eyes, this means that you're seeing a slightly, you're seeing me slightly in the past, right? Because it takes time for light to go from me to you. So you're looking slightly, you're viewing the past in some sense. This concept was taken advantage of by Felix Eberty, who's not a scientist. He wrote a science fiction short story back in the 1800s titled The Stars and World History, Thoughts on Space, Time, and Eternity, where he imagined that somebody who knows that light travels at a finite speed starts from Earth and then climbs on a rocket and goes faster than light, goes all the way to some nearby galaxy, for instance. If you can do that, they would be able to witness the past of what happens on Earth, because he would have overtaken these photons or this light emanating from Earth at different epochs of the history of the Earth. For instance, they can see dinosaurs, the pyramids being built, Jesus being born, and the revealing of the first iPhone. So the upshot is that you'd be able to witness the past by overtaking light. Okay, the hurdle in this story is that it's actually not true. If you were to tell Maxwell of this thought experiment, he would say, no, the equations, yes, they give you a finite speed of light, but they state that everyone's perceived speed of light is the same regardless of what you're doing. No matter how fast you go, the speed of light will always be 700 million miles per hour faster than you. It's kind of counterintuitive. You can never catch up to light. This is very different, for instance, if you have a car going at 100 miles per hour and you get into your own car and go at 50 miles per hour. From your perspective, the first car is going at 50 miles per hour. But that's not how light behaves. This is a very curious property, and it took an Einstein to realize its implications. Okay? He conducted the following thought experiment. He said, let's imagine we have two people, Bob inside a van that's moving at some velocity, and then Alice standing stationary, watching Bob as he goes along. So Alice here is not a giant, she's just in the foreground. So imagine that inside this van, Bob turns on a flashlight from the bottom of the van, which will create some light beam that will take some time to go from the bottom to reach the ceiling. From Bob's perspective, light just went, well, vertically from the bottom to the top. From Alice's perspective, the light would have gone along this diagonal path. Now, both Alice and Bob agree that light moves at 700 million miles per hour. But the distances perceived by Alice and Bob are different. Hence, it must be that the elapsed time for Alice and Bob are different. So this is the phenomenon of time dilation, that the speed of time depends on your motion. Sometimes this is said or described as time runs slower the faster you move. There's a subtlety in this statement. It's not quite correct. Imagine we have two Einsteins, Einstein twins, which will feature more than once in this talk. Supposing that the left Einstein moves at some constant velocity away. If this statement were true, then the left Einstein would not have aged much, while the stationary Einstein would grow old. But this is confusing, because from the perspective of the left Einstein, it's the right Einstein that moved. So it should be that this Einstein, the right Einstein, is younger. So something should break the symmetry. Well, often in physics, when you have this kind of paradox, it means that, or sometimes it means that you haven't formulated the experiment correctly. In this case, what you need is for the two Einsteins to separate, but then for them to come back together to meet and compare results. So we're going to consider the situation where it's the right Einstein that moves. He moves away and then he comes back. So he's going to follow a motion like this and come back. And in fact, in this situation, this Einstein would grow old and he can witness it. The upshot is that it's not really the speed, the constant speed that the Einstein, one of the Einsteins moves that affects the time, but rather the turnaround acceleration that the right Einstein had to do in order to sort of fix the change in time between the two observers. But I emphasize that it's acceleration here that's affecting the time. A few years later, a slightly older Einstein formulated or postulated the following principle called the equivalence principle. He stated that gravity is, with a star, acceleration. There's a direct connection between these two. And the statement is the following. Imagine you have these two rockets and an observer or a person inside these two rockets. They have an apple which they drop. Suppose that this apple indeed drops to the bottom of the rocket. The statement of the equivalence principle is that these two, or this person inside, won't be able to tell the difference, or won't be able to tell whether the rocket is stationary on the surface of the Earth, where there's gravity, or some place far away in the universe, where in empty space, where the rocket is accelerating. The accelerating rocket is the same as a stationary rocket on the surface of the Earth. Gravity is the same as acceleration. But because gravity is the same as acceleration, this means you can use gravity to slow down time as well. So this older Einstein knows about that rule, but this younger Einstein doesn't. So time on the Earth here is slower than the time far away. And he can use, the left Einstein can use this to get back at the right Einstein. Okay, so you can say, I forgot my lunch. he takes a detour, goes back to Earth, spends some time until this Einstein grows old, and then he can go back and meet him, and now they're even. Okay, these ideas are what Einstein used to develop his general theory of relativity. It's which formulates gravity as the warping of space-time. So here we have some ginormous planet being orbited by some smaller object, could be a moon or another planet. The motion of the orbiting planet is determined by how the heavier one bends and curves space-time. This is aptly summarized by John Wheeler as space-time tells matter how to move. It gives you the geometry of space, while matter tells space-time how to curve. Okay, so it's this interplay between space-time and matter. Perhaps the most dramatic example of the warping of space-time happens in the case of two orbiting nearby black holes. This is a simulation from the LIGO collaboration of two orbiting black holes that will eventually merge. And the space-time really dramatically is dramatically warped and curved until the black holes merge and then silence. Brought to you by LIGO. Okay. These gravitational waves were first observed back in 2015 by the LIGO collaboration using this experimental apparatus. It involves two long arms orthogonal to one another with laser beams that run through them. What do you do with these arms? What you're doing is, when a gravitational wave passes through your apparatus, it shrinks or expands one direction, and it does the opposite to the orthogonal direction. So the distance, the space-time, or rather the space distance between this arm can shrink, and the distance here can grow. And you use light to detect that. In an amazing experimental feat, the sensitivity of this detector goes all the way down to a thousandth of the size of a proton, which is pretty insane. Now, let's talk about where in the universe did this gravity wave emanate from? So here is a galaxy that is not too different from ours. If we were to live in this galaxy, the solar system would be roughly 27,000 light years away from the center, somewhere there. And the size of the galaxy is roughly 200,000 light years. And the surprising thing is that this event is nowhere here. The event that they saw is roughly, a whopping 1 billion light years away, almost 10,000 times the size of our galaxy. So it's an event that happened extremely far away, and also 1 billion years in the past. Okay. If this doesn't fill you with awe, you don't have a soul. I'm kidding. Okay. All right. Okay. If we were able to detect it from such a far distance, you might say, okay, it must be that these. I guess that fact was too much for that microphone. Okay. Yeah. So you might wonder, as I said, it's such a this black hole merger happened so far away. So you might think that these black holes must have been ginormous. Well, let me compare the size of these black holes to something you're familiar with. Say our beautiful city, Manhattan. Well, it's actually just the size of a few blocks, just a few kilometers. These although it's small in size, its mass is actually extremely big. The mass of this black hole of this size is roughly 60 to 70 times that of the sun. Imagine taking the entire sun, 60 suns, and squashing them into a few kilometers. Okay. So, so far that was the sort of effect of some signatures that there's a black hole somewhere. You might ask, where do black holes come from? Well, one place in which they come from is from stellar collapse. This problem was studied by a lot of people, most famously Chandrasekhar, and also Oppenheimer and Schneider. You might have heard about Oppenheimer from a recent movie. They say it was good. And the process is the following. So when you have a star, there are two competing forces keeping the star as it is. There's gravity pulling everything in, and there's fusion pushing everything out. At some point, the star can run out of fuel for the fusion, so that ends, and now you only have gravity, which pulls everything in, and if the conditions are right, you form a black hole. I guess you can't really see it very clearly, but I guess that's the point. Okay. All right. So the next question you might ask is, well, have we seen black holes directly? Here's a fascinating video of the motion of stars in the center of our galaxy. These stars are enormous, but they're orbiting something that you can't see, something that's big enough that it's holding all of these stars together. Not just that, it's actually holding the entire galaxy together, or at least plays a big role in that. Okay, but now you might say, well, do we have a picture of it? In fact, yes. Recently, the Event Horizon Telescope collaboration took a picture of the black hole in the center of our galaxy, and this is what they got. The resolution isn't the greatest, but beggars can't be choosers. So these bright spots in this picture correspond to the hot gas that's orbiting the black hole, slowly feeding it. And this dim region in the center is where the event horizon is, where the black hole actually is. The reason why it's dim is because there's no light coming out of the black hole. Kind of a scary picture, to be honest. Okay, next, we're going to talk about the inside of black holes. And that's where things really get wild, so hold on to your hats. The first topic we'll talk about is the nature of the event horizon. So you might have, well, I'm sure all of you know about this property of black hole event horizons. They're often described as the point of no return. But that is extremely counterintuitive. If I'm standing outside a black hole and then I take a step in, why can't I just turn around and take a step out? What stops me from doing that? People often say, well, you can't do that because gravity is too strong. Well, that's actually bogus. In fact, you can have black holes where the gravity at the horizon is even weaker than the gravity in this room. Yeah, I can jump in this room and with no problem. Okay, the actual reason for why you can't escape a black hole is because the event horizon recedes from you at the speed of light. As you try to move towards the horizon grows. Okay, but then you might ask, but if that's the case, why don't I see black holes in the universe growing? I'm saying that the growth happens at the speed of light. Surely that's a very fast speed, and we'd be able to notice it. The answer is that, in fact, the horizon stays put, but what happens is that the interior of the black hole grows inwards. Let's look at a cross-section of the picture in the previous slide. These two blue dots represent where the event horizon is. Okay, I'm looking along the plane. And as a function of time, the interior grows in this way. For somebody inside, it would appear that the horizon is growing or receding from you at the speed of light. Drawing it in one higher dimension, the black hole starts in this configuration, but then the inside keeps growing. All right, so that was the black hole. That was the black hole event horizon. The next often discussed property of black holes is the so-called singularity. It is often described as being the center of the black hole. It's where matter is compressed down to a point. Well, that turns out to be bogus. Singularity is not actually at the center, and matter does not get squished down to a point. That's one thing often said about singularities. The other thing is that it connects to behind the bookcase in your daughter's room. Well, I don't have to convince you that that's not true. The third thing that's often said about them is that they're the end of time inside the black hole. And that turns out to be the correct property or description of what a singularity is. Let me try to make sense out of this statement a bit using a diagram. Here's a so-called space-time diagram. Let me explain it. So time goes upwards while space goes sideways. These people here are not moving in space, but they're moving in time. A lot like all of us here. We're not moving in space, but we're just moving in time. When a black hole forms, what happens is that there's an instability in space-time that causes time to suddenly end at the singularity. So it's where time, it's a region of space, or rather of space-time, where time suddenly ends. So if you were somebody that, first let me also mention this other feature here, this dotted line. That's the event horizon of the black hole. If you were to pass the event horizon, then you're doomed to crash into the singularity where time ends. This person here is smartly avoids the horizon and escapes the black hole, while these two people here ultimately crash into the singularity. This one here on the far right attempts to escape, but they're too late. They've already passed the horizon, and they're going to they're going to die soon. Ironically, if you try to do something like this guy here, and try to accelerate or move while you're inside the black hole, because of time dilation, you actually hit the singularity sooner than you would have otherwise if you just accepted your fate and just floated freely towards the singularity. Okay. Next, sometime in the 70s, Stephen Hawking analyzed what would happen, or how the description of a black hole would change if you factor in quantum mechanics into the description of black holes. Now, I'm not going to describe what quantum mechanics is, because that needs a whole dedicated lecture to do so. I'm only going to tell you about the effects. What Hawking discovered is that there's an instability of the space-time around the black hole, which converts it which converts the gravity or the space-time into particles that emanate away from the black hole. These particles can be made up of things you're familiar with, like light, electrons, and so on and so forth. And they just escape, they fly away from the vicinity of the black hole. Let me emphasize that these particles, they don't come from the inside of the black hole. They originate on the outside and they fly away. This radiation is often termed Hawking radiation. And the upshot is that the black hole slowly evaporates away. Now let's talk about how this process looks like from the perspective of different observers. If you're on the outside, then what you see is that the black hole shrinks. And so the event horizon shrinks until the black hole disappears and entirely. But we're interested in what happens from the inside perspective. Okay, so we're going to go back to that diagram that we used before. And so here's the event horizon. And slowly, the black hole is going to emit these particles. And two things are going to happen. The inside is going to grow. And the size of the event horizon, these blue dots, are going to approach one another. Okay? So it's going to look something like this. Okay? So it's growing in the inside, and the horizon is shrinking as it emits more and more particles, or Hawking radiation. At some point, the black hole disappears entirely. At that step, what happens is that the black hole completely disconnects from our space-time. The inside becomes, sometimes it's described as a baby universe, detached from our own universe. Here's another picture of that. So this is where we live, and here's some detached universe. Well, it's hard to describe. It's not inside our universe, but it's in some sense nowhere. Like this blackness here is the void. It's not empty space. Okay? No, what I mean by void is in its nothingness. Space is a thing. It's an object you can interact with and bend and so on and so forth. But here I'm saying that the universe breaks into two parts. Okay. Oh, yes, please. Yeah, so I won't get into it, but in the future of this detached space-time is the singularity. It all evaporates. From the perspective of somebody living in this universe, all of the energy of the black hole has been transformed into the radiation, the Hawking radiation floating in space. Well, I'm not sure what you mean by beam, but it transforms into this radiation. Okay, no, what you're talking about is a different phenomenon. That's what happens that's what happens when because of the magnetic fields essentially sourced by the black hole and the accretion disk, that channels some of the energy outside the black hole and funnels it in the north and south poles. That has nothing, I mean, that's an extremely interesting effect, but it has nothing to do with Hawking radiation. Yes? You mean the geometry of this? Well, the geometry of this sort of depends on the details. But to sort of first approximation, you can think of it as just being a sphere. Okay. Yes. Okay, if I understood your question, it's yeah, that's an excellent question. Yes, once once the horizon goes down to zero size, that means that you've radiated all of the energy that was in the black hole. So that's it. At this point, there's no more radiation to come out. All of the energy that was in the black hole, all the mass, has been converted into this Hawking radiation. Does that answer the question? Okay. Yes. Of course. No, that's not bogus, but yeah. So yeah. Both. So answer your question. Just for brevity, I focused only on the outside radiation. And yes, there's also for every one of these outside particles, there's also an inside one. They start, so this is a hand wavy explanation, but they start off as virtual particles, but the outside particle, it steals some energy from the black hole spacetime. Remember how I said the gravity around the black hole gets converted into energy? So that outside particle can steal some of that energy in the spacetime and becomes a real particle far away. That's sort of a rough way to understand how the virtual becomes real. Okay. Yeah, please. Okay, so what's next? Okay. So when Hawking was, when he discovered his radiation, he stumbled on a paradox. This is the famous black hole information paradox. So modern physics is built upon the idea that information is always preserved. In physics, you often solve things called equations of motion. Given some data about some physical system now, I can evolve it to the future and tell you what will happen. Conversely, if I tell you the future state, or rather, if I tell you how things are now, I should be able to evolve backwards and tell you how things were. You can always go, you can go in either direction, and you can always make predictions. However, in this situation, it looks like the inside of the black hole and everything you threw into it completely disappears from our universe. So it looks like you're losing the information that fell into the black hole. You might say that the information about what fell inside is contained in this radiation, that it somehow encodes information that fell in. But according to Hawking's calculation, when he did it back in 74, that was not true. So it really looked like information gets lost from our universe every time a black hole evaporates away. So this has been a paradox for, I don't know, almost 50 years. And it wasn't until 2019 where this group of people in a series of papers, including me, finally, sorry? Well, yeah, Joe Polchinski, my late advisor, definitely contributed a lot of the foundations. that led to this work. What we realized is that there's some exotic gravitational phenomena that, if you take them into account, give you a different conclusion than what Hawking suggested. In some sense, the reason why Hawking found why he got this paradox is that he sort of didn't go all the way. He didn't, essentially, his ideas for how to resolve the paradox were too timid. And you really needed to do something extreme and include wormholes to resolve it. Okay? And let me explain how that happens. Let me explain it in terms of a thought experiment. Suppose that George R.R. Martin finally gets his act together and finishes the next in the sequence of the Game of Thrones series, but then he throws it into a black hole, which evaporates away. Okay? So he wrote the book, but it's now detached from us in some baby universe. But you're dying to read that book. So the question is whether you can get access and read it. Well, if you're lucky enough to have a second black hole somewhere in the space-time, we show that there is a way. There is a way to access this book. And it involves doing the following steps. First, this person can build some sort of processing plant, which collects the Hawking radiation from both black holes and processes them in some complicated but careful way. And what we showed is that if you do this, it can induce a deformation of the space-time geometry. It can create a wormhole connecting this black hole to this black hole in the following way. So black hole slowly gets created. It goes into this, the detached interior. He's the wormhole. But in so doing, well, before that, this wormhole gets created only for a short amount of time, and then it disconnects. But when it does that, it extracts the information from what was the inside of the previous black hole, and it's now there. So in order to read his latest novel, you just need to jump. Now he just needs to jump into his black hole. Of course, I mean, he must be really dying to read the book because he'll die. So this is what's actually happening. He jumped into the black hole to get access to the novel, but now both will crash into the singularity. So it better have been worth it. Yes, that's where everything just ends. Space-time just ends. It doesn't end, well, in some sense it ends suddenly, but you'll know that it's ending because of this spaghettification effect. You get squeezed in one direction, but you get stretched in another direction. The forces between your feet and your head become the difference of the forces between your feet and your head becomes so strong that it's going to stretch you and most likely break you in half. Yeah? Yeah, please. No, please, yeah. Yeah, okay. Okay. Okay, so That's an excellent question. The quick answer is we don't know. The more detailed answer is the following. So this calculation, what it shows, yeah, I'll say a few things. What it shows is that the radiation knows about the book in some indirect way. Why? Because all this person did over here was just to process the information. Well, sorry, was just to process the radiation. And just by processing the radiation, it transferred the information from this disconnected, well, this black hole to this black hole. Exactly. It processed the escaped radiation. So what you infer from this is that the radiation must know something about the information. But something that we don't have yet, which we're actively working on but don't know how to get it, is to understand the detailed mapping between the information inside and the states of the radiation. In some sense here, what's happening is there's this notion of holography. The information is in two places at the same time, the inside of the black hole and the radiation far away. There's a correspondence, a duality between those two. In some sense, this is going to sound crazy. In some sense, not that we didn't say anything crazy so far, but in some sense, the inside of the black hole and the radiation far away are the same system. Anything you throw inside gets encoded in the radiation far away. And so the inside of the black hole is secretly on the outside. Okay. Question? So your question is whether the direction of the radiation matters. Or maybe not. Okay, no. Well, it doesn't matter what the radiation is doing, so long as you're able to process it inside this factory. Okay. Yes. Yeah, it's extremely gradual. So even if you have a black hole the size, the one that I showed you, it would take much longer than the age of the universe for it to evaporate. It's extremely, extremely slow. Yeah. Okay. Well, two things. Once the black hole detaches, there's no more energy to emit as radiation. That's it. It finishes. But the radiation is still there and it's traveling. Okay. That's pretty much all of the physics that I wanted to talk about. I just want to end with some comments. Well, why? So just the comment is why do I do physics? Well, it's really for these wild surprises that I do physics. And I personally just enjoy the process of exploration and discovery. You might also ask, when or what was the spark? I can trace it back to high school, where I was taught special relativity in high school back in the Emirates. And it was a pretty advanced class. We learned everything from time dilation, Lorentz contraction, E equals mc squared, everything. And I remember telling myself, how can somebody see all of this and not be a physicist? Well, funny enough, I was the only physicist from that class. But hopefully I've inspired some of you. Thank you.